Welcome to Hot Chips 31. Session 2. Memory.
Our first talk is by Upmem, and Fabrice Devaux is the CTO and founder. He graduated from the Paris 6 University with a master's degree and has experience in CPU design and a number of virtualization topics. At the end of his talk, Gilles Lamot, the founder and CEO, will join him to answer a few questions. So Fabrice?
Hello, everyone. Today we are presenting our next generation general-purpose computing solution at a revolutionary efficiency at today cost. That is processing in memory. PIM at Upmem is straightforward. We just put processor into the memory die. So our product is a DIMM. It's populated with 16 DRAM chips. These are 4 gigabit DRAM chip, and they embed 8 processors. So this efficiency revolution is brought to you through the most standard, the most mundane form factor, DDR4 2400 DIMM module. Once you swap a regular DIMM module with ours, your server CPU is now helped with thousands of additional cores. And doing so allows data-intensive application to be boosted up to 20 times and have their power efficiency improved by 10 times, because most of the data movement will now stay on chip. And all these benefits, you get them at a marginal additional manufacturing cost, because that's just a cheap DRAM process, and we have just a chip being slightly larger. So what is processing in memory? To put processor into the main memory die. So this way, you tackle the dominant cost of data movement. Our implementation is the first ever to meet success condition. It is manufactured on an up-to-date, unmodified DRAM process. It exhibits a mainstream memory interface, DDR4, and it's programmable in a mainstream language, programming language, the C language. PIM is more relevant than ever because you have more data-intensive applications on one side, and on the other side, you have the memory wall and the end of Moore's law. Additionally, you have very big data players, and to them, computing efficiency is paramount, and they have the scale and the skill to adapt software and algorithms. So you have your server, you populate it with our DIMMs, and each DIMM comprises 8 GB of memory and 100 DPUs. That's our processor. And these DPUs are clocked at 500 MHz. And all these things is on a single die. Each chip, it's a single die solution on a standard 25 nanometer process, DRAM process. So on a 128 GB configuration, for example, you have 2 terabytes of aggregated bandwidth and 2,000 cores that help your server. And all these things are easily programmable through a common language, the C language. So that's a DIMM. Each of the chips burns a little more than 1 watt. Okay, but that's, besides this, that's a regular DIMM. So this brings massive benefit. You have this massive speed up and this extremely important power consumption reduction. Despite, as the table shows, the DRAM process is less energy efficient than a comparable logic process. But it doesn't matter that much because the energy cost is dominated by the data movement compared to the operations themselves. So you save a lot of energy by having your local calculation stay on chip instead of moving in and out between your server CPU and your DRAMs. On this benefit, you get them at a very reasonable additional manufacturing cost, which is worth of $300 of extra DRAM silicon. And this gives you a massive return on investment on a lower TCO. Sorry. So what kind of application are we working on? So today we are working on genomics, which is fundamentally pattern matching. So a lot of local calculation here, and we are 25 times faster than the same server without our memory. We have index search in very large database. For example, to find a sentence, what are the closest sentence of a string of 5 different words into a 100 gigabyte data set. We have a throughput which is 80 times higher, and the latency which is 1/100 of what we will get with the same server equipped with regular DRAM. And for analytics, for example, Skyline multi-criteria analytics, we have 14 times higher throughput, and this has been described by a new CR paper presented last fall here. Okay, so the applications which are accelerated have different properties. Some of them are accelerated because we have all this additional processing power because of these additional cores. Some of them are mostly accelerated because of the additional bandwidth, because they were limited by the bandwidth. Usually, that's a mixed bag. But the weight of the contributors vary greatly. Okay, so with so many benefits, the question is, why wasn't it done before? DRAM processes are highly constrained. The transistors are more than 3 times slower than the one you will get on a logic process of the same geometry. Another thing is that your cells, your standard cells are far bigger, 10 times the size. And you have equally the fact that the routing capability of a DRAM process are very bad. You have only 3 metals to route instead of something like 10 metals on a logic process. And the pitch of the metals are very large, 4 times the one you will have on a logic process. So there is no way you can do your regular CPU on such a process. It will be too slow and too big. So because of these constraints, you have to make strong design choices. But that's worth the effort, as we will see. So the first hurdle is that there is nothing ready to make a CPU on a DRAM process. You have no standard cell libraries. You have no SRAM generators on IP. So we had to create a digital library and to incorporate it into the regular digital design flow. We had to design our own SRAM according to our need. The only thing which was already present was the DRAM IP itself, which is the DRAM array. But that's not so easy anyway, because this is not an IP which is intended to be modified. So you have to bring as little as modification as possible, and additionally, that's an asynchronous IP, which has very precise timing window, so we have been forced to generate signals at a higher resolution than our clock, which is not that easy. Another problem is how do we get a processor fast enough to be interesting with such slow transistors? So the obvious solution is to have a deep pipeline. But when you have a deep pipeline, you need a lot of wire because of the bypasses, of operand bypasses, on all the pipe stage dependency. So that's the reason why we have what is called an interleaf pipeline. So our processor is multi-threaded, and the pipeline is such that a thread can have only one instruction in the pipeline at any given time. With this property, this means that you have no dependency between the pipe stages. So no operand bypasses, no stalls. Our pipeline never stalls, and it's as straightforward as it gets. Okay? One consequence of this is that to extract 100% of the pipeline performance, you have to have enough threads running, because you have to fill off the pipeline, the pipe stage of the pipeline. That's something we get at past 11 threads running. So that's our pipeline. As you can see, it is quite straightforward. The operation has more stretch than they would otherwise be because of these slow transistors. To have at least 11 threads running to get 100% performance. If you have less threads, you have less performance, but everything works fine, still works fine. You cannot have a data cache, because these threads will fight for the ownership of cache line, and it wouldn't work. So we have a working memory instead of a cache, a 64 kilobyte SRAM. For design simplicity reason, we have no instruction cache. We have an instruction memory, which is 24 kilobytes in size. And we have DMA instructions, which are capable of moving data in and out between the DRAM array and the working memory or the instruction memory. These DMA instructions are executed by an autonomous engine, so they leave the pipe, doesn't taking any slot in the pipe anymore, and are executed in parallel of the pipeline operation, which executes the remaining threads. So our architecture is fundamentally a custom-passed architecture. That's what DRAM people want anyway. I mean, you have a tile, which comprises one DPU, one DRAM bank, and it's duplicated 8 times. We have a small part of the logic which is not duplicated, obviously, which is a control register and the status register for all these DPUs, and which is connected to the DDR4 interface, also known as the spine. And this one is connected to the 8 DRAM array in a traditional way, as in any DRAM, standard DRAM. So our instruction set is optimized to the kind of realistic implementation we can have on a DRAM process. because of the DRAM process limitation, you won't design an out-of-order processor anytime soon. So we tune our instruction set to be the most efficient in the probable configuration of implementation. So scalar, in order, multi-threaded. It is very important to provide a compact thread context, because when you have 24 threads, then each unused register costs a lot. Besides this, our instruction set is very regular, and it's a very good target for the LLVM Clang compilation suite. Our instruction set is fundamentally a triadic. It's almost RISC. It has some goodies, so it's up to you to appreciate. We have a few 64-bit instructions. So we have 64-bit load and store, for example, and we have some design details, some architectural details intended to help out-of-the-box 64-bit compilation. Because of the routing limitation, our multiplier is a small one. It's an 8 by 8. Besides this multiply limitation, our integer instruction set is rather more powerful than other 32-bit instruction set. For example, most instructions have the capability to jump on their result according to a rich set of conditions. We have shift then add, shift and then sub instructions. And concerning the logical instruction, we have on or XOR, but we have all the variants you can think of with operand inversion, result inversion. And we have a very rich set of shift and rotate instructions. And the most common logical instruction on the addition and the subtraction support 32-bit immediate operand. We made this choice in order to extract the most performance from the constraints we had, and the compatibility was not necessary. We have no operating system running on a DPU. We have so many DPUs, we won't ever need to time share one. One other thing is that the Clang LLVM tools are mature. You get really good code using these tools once you have ported your architecture onto it. And anyway, since we have this multi-threading necessary due to the DRAM process limitation, this means that we have an explicit memory hierarchy. And this would have been an incompatibility point anyway, because to have explicit DMA instructions would have broken any kind of binary compatibility you could ever think of. Concerning security, today we have no particular security features, but tomorrow we will, because when you have the property of not sharing your processor, you are immune to any kind of side channel by definition. Since you don't share your processor, you don't link anything through side channel. So when you have so many DPUs, one important point is that the orchestration, which is done by your server processor, must be very efficient because it has so many DPU to orchestrate. So the control registers of the DPU are mapped into the server, the physical address space. We access them using through cacheable access because it's faster. Even if we have to make the software coherency by yourself, it's faster and most reliable. And we hide all the details about how to make things work on a DDR4 bus, which is not intended for, through a software library, so the programmer is not exposed to all this complexity. For example, the fact that the bus width doesn't match, that the addresses are interleaved, that we have no cache coherency, and that we have no arbitration on the hardware arbitration on the DDR4 bus. And so far, the orchestration overhead has been dwarfed, always dwarfed, by the execution time of our DPU. So this slide is just to address one of the most frequently asked questions. You have the word as seen by the server processor, and to have something meaningful, we have to rotate, if you want. That's not exactly a rotation, in order to feed the DPU with a word in the right orientation. Otherwise, each DPU will have only a fraction of a 64-bit word, and it won't be at all usable. So this is done by software, by the server CPU, inside the cache line, and usually it's entirely hidden by the access because of the out-of-order nature of the server processor by the time the access takes anywhere on the DDR4 bus. So how to program thousands of cores? As usual, you move the critical part of your application to the DPU. You keep what is not performance critical, you keep it mostly in change on the server. And you use the library to dispatch task and collect results, dispatch task to the DPU and collect result from the DPU in order to complete your calculation. So this means that your algorithm need to have a significant data locality inside the 64 megabyte chunk, and you have to organize this in order to get the best result. So that's our SDK. It's conceived in order that you can manage the server code and the DPU code in one go. I mean, it's an integrated solution. And another aspect is that it generates the same code, whatever the target is. I mean, if you have a software simulator or FPGA simulator or our actual chip, actual DIMM, okay? So that's a DIMM. And we will start shipping in October. Today we are using the chip we got to tune everything. In the meantime, we have software simulator, which are available on the cloud, and we have FPGA simulator on the cloud, on-premise. On the Amazon cloud, you can have up to 256 DPU running at 200 megahertz. And when you develop with this system, you will get exactly the same code which will work on a configuration with the actual hardware. So that's our schedule. And a picture of the fab where the chips are manufactured. Okay, so I hope you have questions.
All right, we have time for just a couple of questions. Let's start there.
Hi there, Ian Cuttress from Anantech. You said that each chip was 1.2 watts. That means that a whole 8 gigabyte module is about 20 watts. A, isn't that a bit high? And B, what are you doing in the future to reduce that power consumption?
Okay, the first thing is that on some configuration, we may have external connector to bring supplementary power, okay? That's because we are tangent to, according to the server. Anyway, we have a throttling mechanism, which is to prevent any overconsumption. We have a very small microcontroller on the DIMM, which manages the power consumption of the chip, so this is entirely secure. On the 1.2 power consumption, it's a power virus. Okay, so it's a worst case. It's an application which is intended only to to extract the most power you want, okay? That's the reason why we have this tiny microcontroller, because we don't want power virus to ruin anything, okay? So that's it.
Okay, over here.
Bojan Lai from NCTU. I have two questions, actually. The first question is, do you need to change the memory controller on the host side, or you use the same memory controller? Same memory controller, so you just use the commands, the same DRAM commands to communicate?
There is no need to change the memory controller at all. You have to modify the BIOS to set it to the right parameters. But because, for example, since it's not regular memory, it won't maybe pass the memory test. So we modify the BIOS in this way. But we have no way to modify the memory controller, so it's unchanged, and that's the way it is.
Another quick question. Do the 8 processors in the same DRAM bank, they can exchange data or not?
No.
Or
Okay,
thank you.
Very quick, one last question.
Hi, Tao Zhang from Alibaba Demo Academy. So the quick question is, can these 8 DPUs talk with each other inside the chip?
Same.
No, we didn't envision this because it was not scalable. I mean, okay, maybe it's feasible at 8, and then at 16, suddenly it will be no longer feasible, and at 32, certainly not. So we prefer to serve the wave of the server CPU as a means to connect to all the chips. And it is our network is a server CPU.
So they still communicate through the CPU, and it ensures a maximum scalability in terms of memory capacity.
A quick question. Since the capacity of the PIM is quite small, I understand that there would be a mix of standard DDR and PIM memory within the same system. So you would move data from standard DDR for the acceleration to do the processing over the data, and then back. This is the model?
That can be a configuration. It depends on the way you use our technology. I mean that when we do an index search, for example, the database is resident. It doesn't move away from our PIM. It's 10 on PIM, and we do the comparison extremely fast on the fly. If you use our technology, like we'll use a PCI card with moving in, moving out, that's exactly the scenario you just said.
And the capacity was bounded by the energy budget that we had on the PIM. We wanted to be standard to at least a certain number of Intel cards, motherboards. So it was not possible to build in the first generation bigger capacity DIMMs.
Thank you.
All right, very good. Thank you, Fabrice and Upmem.
Thanks very much.
Thanks a lot. All right, thank you.
Thank you.
All right, so any of you for whom chip design is either circuit design or back end, and not just the software of writing the Verilog and the front end, know what a tour de force getting that chip running at speed and running it all is. So if processing right next to the DRAM isn't enough for you, our next talk will show you how to do processing actually in the memory array. And that's as close as we're going to get in memory. So our next speaker is Hongyang Jia from Princeton. He's got a BA engineering degree from Tsinghua University and a master's from Princeton, and is currently a PhD student at Princeton. His work is in low-power processing for inference. Hongyang.
Thank you. Good morning. It is my pleasure to present this programmable platform for AGI applications based on in-memory computing. For AGI, energy efficiency is critical. Digital acceleration has been essential, enabling 10 to 100x gains by mitigating the huge overhead of programmability due to things like instruction and data fetching and decoding. GPUs amortize this overhead over parallel data, and accelerators like the TPU get avoid of the software instructions altogether. But the gains apply to computation, but not the data movement or memory accessing. In the machine learning workload, we often have these high dimensionality data structures like large matrices, which need to be stored in memory. So in any architecture that separates the memory from the computation, we have this communication cost to move data from the point of storage to the point of computation. And this scales with the size of memory required. How big a problem is this? Here I show some energy numbers for different size of memories and compared with the energy for compute. And we can see that this communication cost is potentially dominant by order of magnitude, especially for a lower precision compute that's getting relevant to machine learning workloads. And this problem is known as memory wall. It affects every level of memory accessing. You just heard a talk that targets DRAM, but our focus is mainly on the embedded SRAM. The reason is that although the AGI models can be quite large, they are still typically smaller than the model we use in the cloud, with about 20 to 50 million parameters. On top of that, a key trend has been reducing the bit precision, with the inference models moving to 4-bit level. Combined with the technology scaling, what all this means is that the AGI models can be comfortably stored in embedded SRAM, even for the modest-sized ASICs. So here's the outline for my talk. I'll start by introducing the basics of in-memory computing, and then I will introduce the challenge that in-memory computing introduces, namely a fundamental trade-off of compute SNR. And next, I will show the approach to high SNR analog compute that developed our group based on capacitors. And then I will show a programmable and bit-scalable heterogeneous microprocessor using this technology. And in the end, I will show the prototype and the measurements. Given that the data movement costs are fundamental, they cannot be eliminated, but they can be amortized. The general purpose architectures employ caching, where the excess data can be reused thanks to the locality that's amortizing the overhead. Specialized accelerators can perform even more aggressive amortization based on the data flow. For example, for the matrix vector multiplications, which are particularly critical in deep learning, the accelerator like the Google TPU use the systolic arrays. Here, small and efficient memories can be distributed with the processing engine so that the data is held where needed as the computation result moves through the array. So instead of accepting the raw bits, move the raw bits through the array, they actually move the computational result, which kind of amortize the movement of the raw data. In-memory computing does something similar, but more aggressively. Let me describe. To illustrate this, I'm going to use this particular structure. In-memory computing performs matrix vector multiplication by exploiting this structural alignment between the 2D matrix and 2D array of memory bit cell. In this architecture, we have prefreeze for 2 modes of operation. In standard SRAM mode, the rows are accessed one at a time to write and read the matrix elements. But we also have this in-memory computing mode, where all the rows are activated at the same time. And this is done by driving the analog signal onto the word lines that corresponding to the input vector elements. The word line signal amplitude modulates the bit cell currents, which then appear either on the bit line or bit line bar, depending on the data stored in the memory cell. And then the current from all the cell accumulate together on bit lines. So if you think of bit line bar as differential signals, this is just like multiplication by -1 or +1, and followed by accumulation. And this is the basic operation of matrix vector multiplications. So this is matrix vector multiplication in one shot. Instead of accessing raw bits row by row, we access the computational result over all rows in each column, so that this substantially reduces the communication cost and energy in order in the factor equals the number of rows, like in this design, 128. But interestingly, this leads to a trade-off that is the computational results generally require a larger dynamic range, which means that they can take on more levels than a single bit. But these levels must be fitted into the fixed constraint bit line voltage swing, which fundamentally reduces the signal-to-noise ratio of the computation. So now the question is, what actually set the noise of the computation? It turns out that in-memory computing often uses analog techniques. This is in order to treat transistors as more than just switches so that we can fit the computation inside the bit cell circuits. However, the transistors have significant nonlinearity and variations, as I've shown in this multicolor simulation. So this non-idealities pose the primary source of computational noise and also the primary challenge that in-memory computing introduces. So where does in-memory computing stand today? Thanks to the interest, there has been a number of prototypes emerge from academia and startups. So here I'm showing the recent designs by comparing the error-normalized throughput and energy efficiency for the neural network accelerators. We can see that in-memory computing can simultaneously deliver more than 10x energy efficiency and throughput. This looks good. But the problem is shown in this plot, where I change the y-axis to the total amount of on-chip memory, which can be a measure of the scale that has been achieved. We see that in-memory computing achieved limited scale, primarily due to the SNR trade-off. But there's only one exception over there, shown as the red star, that achieved the breakthrough scale by addressing the SNR trade-off. So this is the previous design from our group, which transitions to high SNR analog compute. It does this by using the capacitance, but not the transistor currents. Transistors are subject to all sorts of process variation, temperature coefficients, and also the physical sources of nonlinearity. On the other hand, the capacitance only depends on the geometric parameters, which can be well controlled in advanced CMOS technologies. Okay. So here is the block diagram for the bit cells. The horizontal signals are where we want to apply input activations, but this time it's binary rather than analog signals. Then the bit cell performs multiplications with the binary data stored. Since the two operands are binary, this multiplication corresponds to either an XNOR or AND logic operation, and the cell support either. Then the result is stored as charge on the capacitor. And this gives a binary output which ensures perfect linearity. And then the charge from all the capacitors shorted together to give an analog accumulation result. But this result can be highly accurate thanks to the excellent process control and the stability of capacitors. Okay, so here is the actual bit cell we're using, which require 2 more transistors compared with a standard 60 SRAM cell, which causes 80% error overhead. And the capacitor is actually laid out right above the bit cell using metal wiring, thus cause no extra error. So all in all, this multiplying bit cell achieves more than 10 times denser than the equivalent digital storage and logical circuitry. So here is the previous chip we have demonstrated, which achieved the greatest scale of in-memory computing, 2.4 megabits and 64 tiles. I also showed the extremely linear transfer function of multiply and accumulate over 4,608 dimensional column, and also the tight arrow bars showing the standard deviation of 512 columns. The chip achieved the highest energy efficiency and throughput reported for neural network accelerators. We also mapped the neural network with practical scale, like 10 layers in this paper, and in fact, much more, like 20 layers since then. Aside from scale, the next problem that the SNR trade-off limited in-memory computing is the need for heterogeneous computation. In-memory computing primarily addresses matrix vector multiplications, but we can see that there are a lot of other computations that are also required, other than this workloads shown as red bar, which is matrix vector multiplication. But importantly, the difference is that these other computations apply to low-dimensional element-wise operation, which means that they can be well addressed by the conventional digital acceleration, using the conventional approach to the programmability and configurability. But this requires that we have to integrate the in-memory computing into the heterogeneous architecture, together with the digital near-memory accelerator to minimize the data movement cost. This requires that we have a robust functional specification of the memory computing block for better interfacing to other blocks. But the SNR trade-off has limited such specification. So now what we want to do is to address this problem by leveraging the high SNR analog compute. And that leads me to the microprocessor that we are presenting. We have integrated 590 kilobits computer in memory unit, or SIMU, together with a RISC-V CPU, 128 kilobytes of standard program data memory, and also these other peripherals like the efficient memory accessing like DMA, scheduling like timers, and off-chip interfacing like the GPIO and UART. The SIMO makes use of the capacitor-based computed memory array, or SIMA, from the previous design, but we extend this in 3 key ways for programmability. First, we introduced a programmable, configurable word-to-bit reshaping buffer, which allow us to efficiently interface the 32-bit external architecture, processor architecture to the massively parallel bitwise operation performed internally in SIMA. This allows us to integrate the in-memory computing into the standard processor memory space, which significantly enhances programmability. Second, we introduced a digital near-memory accelerator to support the computations surrounding the matrix vector multiplications. This follows a low-power 8-bit ADC that we introduced on each in-memory computing column. Third, we extend the bit scalability from 1 to 8-bit range because different neural network applications require different bit precision. Okay, I'll start by introducing the multi-bit compute. This is achieved via a bit parallel, bit serial approach where multiple matrix element bits are mapped to parallel columns, and multiple input vector element bits are provided serially. So the column performs binary inner product operation on the binary vectors in the way I've described before. And the multi-bit compute is achieved by digitizing the column outputs and applying proper bit weighting in space and in time just by digital bit shifting before adding up the ADC outputs. Interestingly, this leads to the rounding that is different than the standard integer compute. Specifically, we have high column dimensionality, like 2,304 in this design, for better in-memory computing amortization. This can result in high dynamic range up to 2,305 computation levels. But the ADC we use is only 8-bit, which support up to 256 levels. This is chosen to limit the energy and error overhead. So we have intentional loss of dynamic range, which make the signal to quantization noise ratio different with the standard integer compute. In particular, this HC31-R depends not only on the input vector bit precision Bx, not only on the matrix element bit precision Ba, but also on the dimensionality N. You can see here, configuring the dimensionality to 255 perfectly emulates the integer compute. This can be clearly seen in the Bx equals to 8 plot, where we have this blue curve indicating n equals to 255, keep increasing up to 8-bit level. But at higher dimensionality, the HC31-R is still similar to integer compute in the range of interest for typical neural network designs, let's say 2 to 6-bit range. Okay, but what's most important is that this rounding can be robustly modeled thanks to the high SNR analog compute. And this can be integrated into the training process as is typically done for the quantized neural network training, as I will describe later. Okay, so here is the word-to-bit reshaping buffer, which takes the 32-bit data from at the maximum bandwidth of the external buses and converts it into a massively parallel vector. So it does this by taking the 32-bit data and load it into the register array as 4 8-bit chunks. And we have a highly configurable connection network, which takes the 8-bit chunks and loaded them into the register files according to the bit precision chosen for the input vectors. For example, for the 2-bit case here, the 2-bit data is loaded into the parallel register file columns. So the data can be sequenced out in parallel for the bit serial operation. We also have a circular interface at the output to shift data so that the data transferring to the SIMU and word-to-bit reshaping buffer can take advantage of convolutional data reuse. Following this, a sparsity controller, which I won't go into details of, but what this does is to give a sparsity proportional energy saving. I want to briefly talk about the overhead of moving input and output vectors into and from the SIMU. So those data transfers are pipelined with the SIMU computation, and the number of cycles for each depends on the bit precision chosen. The chart shows the number of clock cycles required for the 3 pipeline stages: input vector movement, SIMU computation, and output vector movement across different input vector and matrix element bit precision, Bx and Ba respectively. And we can see that in most cases, the SIMU cycle dominates, which means high SIMU utilization once the matrix element are loaded. There's only a few cases where the data transfer takes more cycles than the SIMU operation, but only by a bit. So here's the microarchitecture of the near memory data path. For throughput and pitch matching purposes, one near memory data path multiplies across 8 ADCs. This also eats the bit shifting and accumulation up to 8 bits for the bit parallel, bit serial approach we use. Okay. This near memory data path computation can be configurable, which can include things like global, local bias, scaling, applying base 2 exponent, buffering the result, and applying nonlinear transforms for the neural network activation functions. So here is the prototype in 65 nanometer CMOS. The area of the SIMU is 8.5 millimeter square with 590 kilobits on-chip memory. The large portion of this is actually a test structure left over from the previous design. The chip achieved the maximum normalized throughput of 0.26 GOPS per millimeter square and the maximum frequency, the maximum energy efficiency of 400 TOPS per watt. This number is for the single bit element. For the multi-bit element, those numbers scale linearly with each bit precision due to the bit parallel, bit serial approach. Our recent work has moved from the 65 nanometer to the advanced CMOS node, and we see the energy and the throughput of this architecture scales just like the fully digital architectures. Okay. So here I want to show some measurement results for the computation on each column. In the figure on the left, I show the transfer functions of the column computation, and also the tight error bars showing the standard deviation across 256 time columns. The voltage supply can be scaled from 0.7 volt to 1.2 volt, with the maximum frequency changing from the 40 megahertz to 100 megahertz. The ADC imposes a small overhead compared with the column operation, and the digital near memory data paths consume less energy than the SIMA operation, indicating a significant leverage from in-memory computing in the heterogeneous architecture. So here I want to show some measured results for the actual neural networks demonstrations. First, we can see that the measured result from the chip match closely with the bit-true simulation that we have. Further, the SQR trend follows what we expected from the simulation. And here are two neural networks demonstrations together with a number of academic and industrial collaborators. We can demonstrate much more networks. But here, we used benchmarking for CFR10 image classification. So we have a network with 4-bit width and activations, and network with 1-bit width and activations. So both network has 10-layer structure as summarized below. And both of them achieve the accuracy as expected with the ideal digital computation. So this achieved the energy per image of 105 microjoules for the 4-bit network, 5.31 microjoules for the 1-bit network, and also the throughput of 23 images per second for the 4-bit network, and 176 images per second for the 1-bit network. This follows the throughput and energy scaling that we expected from the bit parallel, bit serial approach. So to help our collaborators get engaged into in-memory computing hardware, we have developed our prototype into a development kit. So here's a picture of our board showing the connections to the post-processor off-chip memory controller and also the GPIO extension board, as well as the power connectors for measurement. Our collaborators are using this extensively and giving feedback on various applications and software extensions. Of course, to use this board and this platform, one very important aspect is the software. So we have developed a software stack to support training and inference system. It consists of the libraries for design environments such as Keras, TensorFlow, to support quantized neural network training and applying our bit parallel, bit serial approach. It also consists of the libraries to support developing the inference system in 2 ways. So first, we have a development flow which has the libraries in Python and MATLAB, where the top-level control flow can be implemented on the host processor, and the neural network layers can be dedicated to the chip as a co-processor, and this permits rapid prototyping. Second, we have deployment flow with the embedded C libraries running on this chip's RISC-V CPU. It takes function codes from the MATLAB and Python libraries, but it also enables user to deploy fully embedded design, fully embedded inference system on the chip. So our research over last year has focused on the algorithm for optimizing software mapping, which means that we have been developing compilers and automatic optimizers, which takes the designs from Keras and TensorFlow and then map them directly to the chip. So here I want to show some quick illustration of our training and inference libraries. So for training, we have implemented the superclass of each neural network layers in Keras. And this includes arguments for the quantization level. It also includes a flag to let user choose whether you want to model the quantization in the chip's bit parallel, bit serial approach, or using the standard integer approach. This enables evaluation and comparison. And for inference, we have this Python and C libraries, which again, you can see that we have arguments for quantization level, but also have a flag to let user to model the chip's computation in software on the host processor so that the development flow can proceed even without the hardware connected. We are very happy to share our libraries with you. If you're interested, please do find me. So here's the conclusion. Matrix vector multiplication is a fundamental operation in embedded in AGI applications, which suffer the data movement cost due to the high dimensionality data structure. We have exploited the capacitor-based in-memory computing to enable high SNR analog compute, which enables scaling up of the in-memory computing designs. We have demonstrated a programmable in-memory computing heterogeneous platform with these supporting software libraries on which neural networks with different structures and bit precisions get identical performance comparing with the software implementation, but with orders of magnitude energy savings and speed up. So our recent work has moved to the advanced node, which shows energy and density scaling similar to standard digital logic. Okay, and that's all. Thank you for your attention. Any questions, welcome.
All right, thanks a lot. That's amazing technology as well. We have some time for questions if there are any. And it looks like there may not be. All right, thank you very much.
Thank you.
All right, well, we've gotten the computing about as close as we possibly can to the memory cells there. And now we're going to zoom back out, and this next talk, Intel will talk to you about their Optane memory, so how to bring huge amounts of memory next to, very close to, a traditional high-performance processor. Our two speakers are Zhane Xu, who is a senior architect at Intel, senior memory architect. Jane actually presented at Hot Chips 15, a networking chip, and is back now to tell you about memory. She'll talk about the architecture. And then Lily Looi is going to come out and talk to you about performance. Lily's a senior principal engineer, and she has 28 patents and degrees from the University of Michigan. So Jane and Lily, thank you.
Thank you, Fred, for the kind introduction. Good afternoon, everybody. My colleague Lily and I will be presenting Intel Data Center Precision Memory. First, we would like to acknowledge our co-authors and co-workers for defining, developing, and validating this technology. Let me just pause a few seconds for you to read. A new memory or storage technology never comes easily. Looking back, the last technology, NAND, was introduced 32 years ago. Further back, DRAM was invented 5 decades ago. At Intel, we have been working on a new class of memory for years. We enabled it with 4 new things: new interface protocol, memory controller, media, and software stack. I will walk through most of them in some details. This is the current memory storage hierarchy. Data gets less frequently accessed is placed in DRAM, with access latency around 70 nanoseconds, but with a very limited capacity. The cooler data gets accessed less frequently, is placed either in non-SSD or hard drive, with access latency around 80 microseconds or 100 milliseconds. Today, the data set is getting bigger, and only a tiny fraction of all the collected data got processed and utilized, largely due to this memory and storage gap. In order to close this gap, some solutions could include the DRAM needs to get a whole lot bigger and cheaper than the current pace, or the storage needs to get a whole lot faster. Since neither of these two things are going to happen in short term, there's a gap. Here's where we are stepping in. Intel Optane data center persistent memory along Optane SSD, we can help unlock a user for data processing with access latency around a couple of hundred nanoseconds. Lily will provide more details on that. And meanwhile, it also offers SSD-like capacity to turn big data into even bigger results for performance and cost optimization. The foundation of this memory technology is the Optane media. The Optane media takes full advantage of 3D cross-point architecture. It can stack in 3 dimensions, so you can imagine the density can be scaled from generation to generation. We put microscopic material pillars in between the metal interconnects. Each pillar has a switch that allows us to use it as a memory, can access each individual bit or a word of memory. Meanwhile, it is also a storage element that allows us to use it as a storage device. By varying the bulk resistivity of each pillar, that can represent whether we store 0 or 1. So each switch, it can switch the speed, can be 1,000 times than NAND with super high endurance. And meanwhile, it is still maintain a few times higher density than DRAM. This Optane media really brings the best of both worlds for us to enable data persistency, even with power loss. That is very important for large data set, because after cycle, you don't really need to rebuild the data set. For the first generation, we offer ranging from 128 gigabytes up to 512 gigabytes. Now let's see how we put the Optane memory module together in a DDR form factor showing on the right-hand side. Data buffers are needed for high-speed I/O and for signal integrity. We also use the SM bus for device discovering, and we also use that to do polling for thermal temperature periodically. Address direction table in DRAM to track the address mapping between the system address to physical address on the media, because we do some wire leveling for media management. So at the meantime, the AIT content is also being copied in the Optane media in case there's a power loss. PMIC generates all the power rails for controller and for the media. We store firmware in SPI flash. In case there's a power fail, we also have energy stored capacitors to make sure we have a safe flash for all module queues when there's a power loss or other events like unplanned events. The heart and soul of this memory controller module is the controller itself. In this controller, we have many innovations for performance, security, and reliability. It has an ECC engine, encryption engine, media management engine, buffers along the data path. It also offers power and thermal management. Users can set power limit in case they have a different thermal solution. So Optane Media has 11 parallel devices for data, ECC, and spare. And I already mentioned the capacitor. The transfer size on the CPU host is 64 gig, is a single cache line granularity. On the media side is a 4 cache line granularity for ECC efficiency. So this is the software stack. Our software team actually created the software model, the programming model, using existing API. These APIs are very useful for memory mapping. And actually, they are at the heart of the programming model published by SNARE. A persistent memory aware file system can set up the memory, persistent memory location, so you can do direct load and store to it instead of do paging access with the traditional storage. So with this technology, actually, you can just treat it as memory the same way you do today. Now let's talk about another key feature, which is combined with the program model. We also have a hardware feature implemented called ADR. That stands for asynchronous DRAM refresh. So the flow I can quickly go over is the platform logic can trigger this ADR, and then the ADR signal will send to PCH, and PCH start ADR timer, and then generate ADR sync signal to PCU in the CPU complex. And then PCU will generate the signal to memory controller, tell memory controller to flash write pending queue. And after the timer expires, the PCH will assert a complete signal. So how we use this, we have two basic modes. The first mode is memory mode. The memory mode is to mimic a volatile DRAM, but with much bigger capacity. DRAM is used as a write-back cache, and it's also called a near memory. And the Optane memory in the volatile area is also called the far memory. So between far memory and the near memory, the ratio can vary. We first recommend is 8:1, but the operational ratio can be much flexible than that. The next mode is more excited and more impactful. That takes full advantage of the architecture. So in this mode, actually, the DRAM region and PMR region are visible in the memory space. So in this one, we already laid the foundation with the software stack and the ADR feature. In contrast, storage doesn't have in place persistency because you have to access them in blocks. And it is cache coherent and also support DMA and RDMA for data transfer. On the right-hand side, we show there are a couple of instructions you will use, so software will maintain. Make sure we send all the flash information into the memory controller, and memory controller will make sure we will flash to media safely. Next, Lily will, based on these two modes, talk about performance. Lily?
Thanks, Jane.
Yeah.
Can you hear me? Okay, so I know I'm the last person in between lunch and this talk, so let me jump right into it. Oops. I'm going to talk about 3 elements of performance. One is the raw performance of the module itself that Jane has just described. One is how it performs in a system in memory mode, and the last topic will be how it performs in a system in app direct mode. So we'll start with my favorite metric of latency. So this graph shows latency. On the y-axis, it's latency, this load to use measured in a system. The top line is an SSD, and if you start at the left side, that's the raw latency, the time it takes for the CPU to get the data that it's requested, and it measures in about 100 microseconds. The second line in the middle, that is the latency of an Optane SSD, and it measures in about 10 microseconds, so an order of magnitude lower. The bottom line is the Optane DC persistent memory, and for this 256-byte test, granularity test, it's at 180 nanoseconds, so a couple orders of magnitude lower than any of the SSDs. That's the left side, that's the raw latency, so there's huge, tremendous improvement over SSDs. Now, it's not quite as low as DRAM, which is about 70 nanoseconds, but at 180, that's at least in the ballpark and interesting to use. Moving on the x-axis out across, that's the bandwidth. So as you've increased the amount of traffic, and this is a read-write mix of traffic, the latency for all these devices stays at that idle latency until you get out to the end where it's getting saturated. So that's what the latency looks like. This is the same graph with more data points. So we've got different granularities. And in all these cases for the SSDs, they're all 4K granularity because that's what the SSDs operate at. So in addition to the 256-byte byte granularity, there's also a 64-byte granularity. That data point is added. And there's also 100% read traffic in addition to the read-write mix. So you can see how it varies. And in all these cases, we're still seeing the latency between 180 nanoseconds and 340 nanoseconds, still meeting that orders of magnitude. Okay, moving on to memory mode. I'd like to expand on what Jane described and go through the transaction flow. And this is both between the CPU and the Optane persistent memory, because that's going to apply to the performance. The middle picture here, this is what happens when you're using the DRAM as a cache and it hits in the cache with the Optane persistent memory as the far memory. That's the actual memory that the software will see. So in this case, the CPU issues a read request. It's sent to DRAM. It returns back to the memory controller, and it does a quick check to see whether the data is in the DRAM cache. In this case, it is, so the data is returned directly to the CPU. The example on the right is what happens if you've missed in the DRAM cache and you need to go to the Optane far memory. So it starts out the same, and a request is issued to memory. Once it gets back to the memory controller, a quick check is is done to see if it's in the cache. In this case, it is not. So a request is issued out to the FAR memory, the Optane memory, and that's what's returned. From the software perspective, it looks just like a load. It just took a little bit longer because it missed in the cache, just like any other caching architecture. So here's some measurements on the memory mode performance, and this is bandwidth. Actually, I should say one thing. This shows that the latency, if you're hitting in the DRAM, is the same as DRAM. It doesn't show, but I'll show you on the next slide, that it also gives you about the same bandwidth as DRAM of the same frequency. So that's what we see here. This is measurement of a synthetic traffic generator called MLC, and it's generating 100% reads, and we're varying two things. One is we're varying the bandwidth that's requested, and then we're varying the size of the buffer. And by varying the size of the buffer, we're varying how often we hit in the cache versus miss. The top line shows the most intense workload that's requesting full bandwidth, and then the x-axis sweeps across the cache miss rate. So starting at the left, where everything's hitting in the cache, the bandwidth is about 110 gigabytes per second. It's very close to what you would get from DRAM. As we move to the right, that gray line drops, and that's because you start missing in the DRAM, and you need to go fetch the FAR memory. And just like any caching architecture, the bandwidth will drop, and there's a degradation there. So that's kind of the interesting spot to really analyze. Now that's for the most intense workloads. A lot of workloads don't request the full bandwidth all the time. It depends on how compute intense it is and other factors. So the orange line in the middle shows a typical workload that has a medium bandwidth request. And in that case, even with cache misses, the bandwidth stays about the same. So no degradation in the medium. And similarly, in the low demand workloads, there's no degradation as you start missing in the cache. And here's some configuration details that you can take a look at on the posted version. So we have this giant memory. What do we do with it? It goes up to 6 terabytes in 2-socket. There's a couple of things we can do, and more ideas are coming out every day. One thing is to increase the size of the data buffer, or the data set that you're operating on. So if you're running on a database, just increase the database to something very large. And this may enable consolidation or things that were split across servers. They might fit all on one server in that case. So that's one thing that you can do. Another thing you can do is run multiple of these large data sets in parallel in a virtualized environment, so in different virtual machines. In this example, we tried both things. So we are running the Redis database, which is a very popular in-memory database, and we're using a very large database size. The first experiment is a 90 gig database. We're putting one of these Redis instances in a virtual machine and then replicating multiple virtual machines, each running their own instance of Redis until we run out of memory. What we see on the red line is at the left, 768 gig system, we can run 7 of those VMs. Scaling as we move towards the right, it can go all the way up to 56 VMs at 90 gig. That's on the 6 terabyte system. And it's the large capacity that made that possible. Now, just to make sure that we didn't break anything, we did obviously measure this. And we saw as we increased the number of VMs running on the same system, the throughput increased because there's more traffic, there's more requests accessing the database. And that's a good thing. The latency also increased, but in all cases, we were well under the 1 millisecond SLA that's required for quality. And the graph on the right shows that even at 6 terabytes with 56 VMs of 90 gig, we're only at 0.67 milliseconds, which is well below, the 1 millisecond SLA. We also did the same experiment with a smaller database size and a smaller VM size of 45 gig. Similar story, it scales very nicely. We meet all the latency requirements. Once we exceed that dotted line, that's when we start doubling up VMs on the same core. So in that case, the slope of the line changes, but it still does continue to scale and still meet the SLA, the latency. More configuration details. Okay, so the last section is on AppDirect, and I'm going to go through the flow here. The first one is, remember, AppDirect is where you've got DRAM memory, which is volatile as the software sees it, and then software sees this new space. It's also memory, but it's persistent, so it knows that it's permanent. So in a traditional read, and that's this middle box, if you missed in DRAM and you needed to go access what is on the SSD, that's a page fault, and first you'd run the software stack, the storage stack, to figure out where that data is on the storage. And then there's a 4K transfer from the SSD into memory. And then finally, the data is returned. So the CPU's request for data finally comes back, the CPU core. A lot of overhead, but that's the traditional way that a page fault would happen. With AppDirect, and if you remember the software stack foil that Jane showed, this would be on the far right where it's a direct access to memory. It just issues the request. It goes out to far memory, and a single cache line is returned. There's no 4K blocks involved, and that data is consumed. So very simple. And to take full advantage of this simple flow, software changes are needed. You can also make this work without software, but to take full advantage, you need to do that. So here's an example. Now, Redis is typically an in-memory database, but you can turn on logging, and then you have a lot of benefits, like you can reboot without having to reload everything. So in this case, we're taking Redis, we're turning on the logging, and we're making software changes to speed up the logging. On the left, this is a traditional Redis with logging, or AOF. And the data is in DDR, just like normal, in-memory database. The blue is the keys, and the green is the values. So that's the full database. In parallel, every time you make a change, a copy of the change is saved off in the SSD. In a lot of systems, the copy in the SSD is the performance limiter. So that's the way it works today. The software change is to move the biggest part of that data that was in DRAM into persistent memory. That does two things for you. One, you don't need so much DRAM, which is very high cost. And the second thing is, now that you've moved it into persistent memory, it's persistent. You don't need a full copy in the SSD. So you save on having to save that copy into SSD. There is still some management in the SSD with the AOF pointers just to keep things aligned, but that's much smaller. So by moving the data from DRAM to the persistent memory, we're seeing a logging optimization of 2.27x. And this is on the Redis benchmark set, 100% writes. Another way to take advantage of the AppDirect is by turning the AppDirect into a local I/O cache. Now, local I/O cache is not a new concept, but putting in persistent memory is because it gives you the much larger capacity. And in this case, comparing putting the I/O cache and accelerating the I/O versus going out over network and to storage is a significant improvement. Even compared to a smaller DRAM I/O cache, there's an 8x improvement. When you're running a decision, this is a decision support benchmark with looking at the I/O intensive queries in there. I think there's there's 9 queries there. So those are just 2 examples how you can change software, or we changed software and saw a big performance boost, taking advantage of the fact that it's persistent. And the added effect is also saving on so much DRAM by moving things into the persistent memory. Okay, to summarize, the Intel Optane DC persistent memory closes the gap between DDR memory and storage. It's architected for persistence, and it provides very large capacities, which scales workloads to new heights and new usages, and some of which may not have even been discovered yet, but both in terms of data set size, in terms of number of parallel instances, virtual machines, just new heights. It is optimized for performance. It's got the orders of magnitude faster than NAND, lower latency. It's memory mode for large, affordable memory, and AppDirect mode for persistent memory. And that's all I have. Thank you.
Please don't go to lunch yet. This was the last talk, but we have a quick memorial coming after the questions period, so appreciate it if everyone would hang around. It'll just take a moment. So we do have time for some questions. Thank you, Lily and Jane, first. Are you coming up for a question? There you go.
Hi, I'm Amarnath from Xilinx. I have two questions. First question is, can you share the raw performance details of the media device itself? And the second question is it possible to bring the media device either in package or on chip? And do you have plans for it?
So I'll take the first question. You can take the second question. So the media, as Jane showed, is embedded in the memory. So the best way really to understand the media is to measure it at the module level. So there was two numbers that I showed. The 180 nanosecond also includes some buffering, which were in the block diagram of the architecture. The 340 nanosecond, that's the latency of accessing the media.
So, could you repeat your second question? There was some noise.
Is it possible to get the media onto the chip or in package?
Well, that's a good question. I think at this point, I can say that have to stay off the chip. But for future technology, for future technology development, we maybe can bring the possibility, but not now.
Thank you.
Okay, Charlie.
Hi, Charlie Demergen, Semi-Accurate. During the talk, you mentioned spare chips, you mentioned ECC, and so on. One of the areas that I haven't really gotten a clear answer for is how where leveling and stuff is done at the chip level, at the module level, and at the system level. Can you expand on that a little?
Yeah.
And is there spare capacity on die?
Yeah, there's a spare device actually in the module, and so the where leveling is across all the devices.
Okay.
I have a question more about the basic structure of the memory itself, rather than the application level performance features. Has it ever been covered in paper yet that should look somewhere to actually find out, have you guys said that this is yes, like it's a chalcogonide phase change memory, it operates like X. Is that something that's public yet, or are we just kind of like looking at this like a black box?
I think we have disclosed the information. Actually, the things change is really the bulk resistivity. Maybe you can treat that from a phase change side, make some connection, but we really think the most effective thing there is really the bulk resistivity. That's how we, actually, that's how that works, and that's how we describe it.
Okay. And one quick question about the DRAM caching mode. Have you guys published anything about the tag and line structure for the reads that are hit for DRAM, or is that something with the micro benchmark to deconstruct, or is there any literature on that yet?
No, we haven't. Actually, this is the first time at a big conference we disclose all the information, so you won't find that anywhere else.
Okay, thank you very much.
All right, one last question.
Yeah, I just had one question associated with your latency chart earlier on, where you showed a different random read latency for 64 bytes versus, I think, 2K. If it's random, why is the latency different? Or maybe you could explain that.
That's a good question. So there are actually buffers on the controller that Jane was describing, and that will buffer up to 256 bytes contiguous. So if you're doing a 256-byte granularity access, even if it's random, you benefit from that buffering. And that's why it's a lower number.
Okay, so the 256, or sorry, the 2K example was picking a random 2K block and then reading the entire 2K?
Yeah.
Or how does that?
Well, there was 4K for the SSDs,
4K.
and then 256-byte for the Optane. But if we did a 4K, we would get about the same.
Okay, so you showed 64K and 256K, or sorry,
4K.
sorry, 64 bytes and 256 bytes.
Right, right.
And 256 bytes, it gets essentially a hit in the DRAM cache. Okay.
Well, it gets a hit in the buffer on the controller.
Right, okay, okay, thanks.
Yes, correct.
All right, so thank you to all the speakers for 3 really wonderful talks.
Thank you.
Thank you. All right, so now Forrest Baskets, one of the original founders of Hot Chips, is going to come out and tell you a little bit about some history here and a little memorial.
So in spring of last year, Robert G. Stewart passed away. Bob Stewart was the founder of Hot Chips, and we wanted to say a few words about him. I think we have a short video. This is Bob right here, and you remember, I'm sure many of you remember his bell that he summoned us from intermissions.
Hi, I'm Bob Stewart, the guy who started Hot Chips. It's been a long time since then. The first conference was in 1989 up at Stanford in Kresge Auditorium. We started the planning for it about a year earlier, and the whole idea developed when Glenn Langdon, who was at that time the TC chair for microprocessors in the IEEE Computer Society, asked me, Bob, don't you think we should have some tutorials out here? And I answered, well, no, I think we should have a conference on Hot Chips. And that was the very start of the whole process of creating this conference.
So I just wanted to try to indicate what problem Bob Stewart was solving. It was an innovative solution, and I think all of us have benefited from that solution now for 31 years. It's been fantastic. Back in '88, there were conferences where innovations were presented, and they were organized by some commercial organizations. The conferences were relatively well attended, 200 to 300 people, and they were expensive. 30 some odd years ago, they were typically $700 for registration fees. And as a consequence, although there were really interesting innovations presented at these conferences, they were mainly attended by VPs of engineering and vice presidents of various kinds, especially marketing people. And they were somewhat inaccessible to the working engineer. That was the problem that Dr. Bob was really trying to solve. And I was one of the people that was fortunate to be called by him and asked, let's figure out how to do something where we use a relatively inexpensive venue like this one and have sponsors who pay a lot of the bills and can provide a conference where the registration fee is such that your supervisor will approve your attending. And that's what we've been doing now for 31 years, and we wanted to be sure to thank Bob Stewart for having that innovative solution to a problem that is now behind us. So let's all thank Dr. Bob. That's it. Lunch.